here comes 6.1. Chapter 6, the whole chapter is called, like, I'm spacing on it right now. Actually, I don't have the book in front of me, but I think it's more integration techniques, or like more integration uh, concepts, or something of kind of feels something like that. Turns out 6.1 is the only section from chapter 6 that we do. This is our final section on integrals. Then we move on to a few sections in chapter 7, which actually are derivative focused. It's the area between curves. This could have come very easily in chapter 5, but they felt it fit a little bit better under this title of other things you can do with integrals for whatever reason. Okay, so 6.1 is the area between curves. Here's what we're going to do. Imagine you have two functions. You've got, apologize for the shadows, you've got f of x and you've got g of x maybe going underneath it, and we only want to find the area in between. Okay, very, very common, a lot of applications here. Only the area between the functions. Okay, well, how are we going to do that? So, well, let's think. Couldn't we find all of the area under f of x from a to b, then find all of the area beneath g of x from a to b, and then subtract? If I find all the area all the way down the x-axis under f of x, and then I subtract the area under g of x, wouldn't I be left with just the portion in between? I would. Okay, so that's exactly what we're going to do. We're going to do the integral from a to b, f of x dx. Then we're going to subtract the integral a to b, g of x dx, and that will give us just the portion between. Now, if you remember the properties of integrals, if you have the same limits and we're subtracting, we can combine this into a single integral, like so. A to b, and often you see a big bracket, f of x minus g of x dx. Okay. And we say area here, area equals. All right. One thing to be absolutely certain of when you're setting these up is that you put the function that's on top in the first position and the function on bottom in the second position. So top minus bottom. Top minus bottom. All right, for obvious reasons, you got to do that. Before we get into our first example, I want to present just another case. Sometimes people ask, but what if g of x is below the x-axis? Let's think through that. What if your drawing actually looks like this? So f of x is fine, it's all positive, no big deal. But g of x actually falls down here. And this is the area that we want. And people think, well, then aren't we adding? Aren't we taking the area beneath f and adding it with the area for g, where before we were subtracting? If this is the case, should we add? And well, I mean, you got a good point there. Yes, we should add. However, when you calculate area underneath the x-axis, it comes out to be negative when you do the definite integral. So in order to add, if it's negative, you actually want to subtract, because you want to subtract the negative so that you end up adding. So it's not a different formula. It's the same formula. Let me get it back on the screen. You would still subtract g here because that integral is going to be negative, so subtracting it would end up adding. So to get that area, we still use this. That's so awesome. That is so awesome. Also, sometimes, you might get some really cool cases where like g starts negative and then goes positive. It's still the same formula. All right, I'll stop with that. Okay, if you want to talk more, we can talk about it in the live meeting. Let's get to our first example. Okay, when I show you this, I want to encourage you, maybe put this video on pause, open up Desmos on your computer. We're going to really take advantage of our online free graphing tool, Desmos, DESMOS.com. Go there so you can graph these things, get an idea of what they look like, really to distinguish what's on top and what's on bottom. Okay, so this is all they're going to tell you. Find the area bound by the curves, and then they're just going to list the curves. Okay, so y equals 2x plus 6, that's one of them. Y equals 3, and then x falls between 1 and 4. All right, so I'm just going to show you a drawing, a sketch that I did on the page. But right now in Desmos, go in and put these two functions in there, y equals 2x plus 6, y equals 3, and you should get something that looks like this. Okay, so here's my x-axis, here's my y-axis. 2x plus 6 goes upwards like this. It passes through 6. And then y equals 3 is obviously the horizontal line there at 3. Okay. But then we have these x values. So you also want to graph x equals 1, the vertical line, at each endpoint. X equals 1 and x equals 4. Graph these as well. And when you do, x equals 1 is going to be about right there. And x equals 4 is going to be somewhere out here. So you've got these 4 boundaries. Okay. Now, the first part of the problem is just figuring out which area do they intend us to try and find. And it's a good idea to get a sketch and to shade it yourself. The area bound by the curve. So here's the idea. These 4 curves are the 4 boundaries. So the region is going to touch all 4 of them. It's going to be bound by each one. Okay, so sometimes the region is obvious to some people. Sometimes it takes a moment. But what region, what should I shade so that I'm bound by all 3? So I got the line there, I got the horizontal line, I got these 2 vertical lines. So it's this kind of trapezoidal region. It's almost a triangle except for the tip down there. It's right there. So I'm caught between my 2 vertical lines, you know, at 1. Did I put 1 back here? What am I thinking? What was I thinking? Wow. Wow. I graphed -1. Okay, well, it's too late to restart the video. We just got to go with it. So there's 3. Okay, well, 1. Let's put that 6 over here. 1 is on the other side. Right here. There it is. I don't know why I was thinking -1. Okay, so here's the trapezoidal region that we want. It's between the 2 vertical lines and it's between our 2 functions. Okay, perfect. That looks really good. That's what I had in mind when I thought up this problem. Okay. Oh man. Perfect. We got it. So now we can look what's on top, what's on bottom, and we can set up our integral. Here we go. I'm going to just pull this up a little bit. Let's go for the integral. So we say a equals area equals, the bounds are 1 to 4. That's where we start and end, 1 to 4. Top minus bottom. So of course the top here is the 2x plus 6. The bottom is the 3. So top minus bottom. That's really what's new about this section, is just now we got to set these things up given, what they tell us at the beginning. Then it's just a matter of executing the antiderivative. First, let's go ahead and simplify what's inside here. We don't have to keep these separate. We can simplify that, f of x minus g of x. So definite integral 1 to 4, 2x plus 3 dx. Take your antiderivatives. Since we've been doing these now for a couple of sections, I'm going to assume you guys are doing pretty good, and this is a simple one anyway. 2x came from x squared, 3 came from 3x, and then we evaluate from 1 to 4. Okay, now it's just a matter of plugging in the 4, subtract, plug in the 1. All right, so plug in the 4. Area equals 4 squared plus 3 times 4 minus 1 squared plus 3 times 1. Some of this is a bit dim on the video. Grab your calculator at this point. I just plugged that whole thing in. I got my area to equal 24. Okay. I think this is a great place to stop this video. We've got a few more, so it turns out there are some different styles, different examples. So we've got a few more to work through to see all the different possibilities. See you there.